Great. Well, good afternoon, everyone. I'm Professor Ron Fearing. Professor Archuk has invited me to give you a guest lecture today. It's actually not a guest lecture, just to cover the regular material. And we're talking today about the sampling theorem, which is in Chapter 7 of Oppenheim and Wilsky. And I think you've been dealing with digital signals for quite a while, probably from the 16A, 16B series. And what the sampling theorem, the discussion in today's lecture, is to really get down into some of the technical details for when you can just take a continuous time signal. We're surrounded by the real world's full of continuous time signals. When you can take those signals and capture them in some way and put them on a computer and process them and output them and have any hope that what you're doing makes sense mathematically. So we're looking at the principles that underlie this basic digital signal processing system. Where there's some analog or continuous time source. Oh, let's call that x of t. Typically, this would pass through a low-pass filter called the anti-aliasing filter. You'll see when you talk about anti-aliasing, why it's called that. This is typically a low-pass filter. This goes into a block, an analog to digital converter, which converts analog voltage values into digital numbers stored as on your computer as ints or shorts or floats or doubles or what have you. This would typically be x of n, and I think notation in the notes is d of n. So this is discrete time. It's also discrete amplitude, but we won't really need to worry about that. You can actually handle the discrete amplitude if you've taken 126, is that the error you get from quantization that could be considered as some sort of noise that's added on. So we won't worry about the discrete amplitude level here. Then you have your CPU does whatever calculation it might want to do. Filtering, multiplication by other signals, changing the frequency. That could be basically be this could be implementing your cell phone function here, doing a descrambling of the signal, figuring out what the information content is, voice recognition, what have you. General algorithm here then goes to a D to A, digital to analog converter, and then finally back to continuous time. The input here, we might look something like this, and then in discrete time we'll get just numbers. Maybe it looks something like this, just doing it very approximately. And then finally, when you get the output here, whatever is being done on this, typically a digital analog converter will have something called a zero order hold, which we'll mention in a little bit. So the output might look something like this. I'm just representing what it is. I'm not saying what particular signal it is. You could have any function you want, of course, inside your computer. Okay, so what we're going to talk about in the sampling theorem is what's going on as we convert from here to here. That sampling operation does some interesting things, and we can talk about that. So I guess, yes, question. So what we're going to find out is that for the system to work, we have to deal with band-limited information. So what happens is that, just think about, if my original signal was, let's say I had just 2 spikes here, and that's a possible signal. This is my x of t. Let's say I sampled it right here. What do I get? Get 0, right? So I've got a continuous time signal, and now I sample it and I get nothing. So obviously there's no information there. So the only way to ensure that we capture all the information we need is we have that low-pass filter in the beginning, and that's called the anti-aliasing filter, and that'll make sure that the input is changing slowly enough and smoothly enough so that you don't miss any important detail. But there's also something else going on there, right? You're saying I am not going to be able to capture the very rapid changes in the input signal. I'm going to throw them away with that low-pass filter and pretend they don't exist, and that information is gone. You can never get it back. But it turns out that's the important compromise. We'll talk about that. If you don't make this, if you don't put that filter on there, now what happens is that all that high-frequency information, you're taking samples of it, but you don't have enough samples, and it just ends up as looking like noise. Your signal looks really, it becomes corrupted with, in effect, noise, and so you lose your information there as well. Great question. Other questions? Okay. So I assume we've gone through all the Fourier transform properties. So you've done multiplication property. So properties x of t times p of t. What's Fourier transform of the product of two signals in time? I'll tell you that this is x of omega, this is p. If x has Fourier transform x of omega, p has Fourier transform p of omega, what's the Fourier transform of the product? It's going to be a convolution operation. Yep. So it's convolution x omega, p of omega, and there's a constant in front. 1 over 2 pi. Okay, great. Okay, so we need that. We need that property when we're doing the sampling. The other property we need is we're going to model this sampling operation here by this sort of artificial mathematical construct, which is a train of impulses, t, 2t, and t. So this is a infinite train of impulses defined it mathematically. Let's do some from k equal minus infinity to infinity of delta. Let's see. What goes in the brackets here for the repeated impulse train? T minus kt, right? So at every multiple of t, you get an impulse. In practice, this is the idealization for sampling. Reality, you'd have something that looks more like that, which would have a finite width, so it's a real signal. And is anyone into circuits? Anyone done 105? Yeah, okay. So don't look at this if you're not taking circuits. But the sample and hold, actually everyone knows what a capacitor is. There's a sample and hold. So this is x of t, and now this runs at every t, 2t, 3t, ... This voltage right here is, I would say, very closely related to xd of kt. So very simple operation, just a switch in a capacitor that samples the input signal. This has got some extra complexity with it, like how we'd have to get into a lot of the circuit details for how long the switch opens for, and the capacitor charging, and the input impedance, and all that. The output here actually looks more like this, which is what I drew here. Okay. So again, a detail, we can add that detail in later, but gives you the basic idea that, I can now, with an A to D converter, I can read this value, that value, that value, after I've sampled it. Okay. So that's what's going on underneath. Question on that? Okay. So back at the math. So we have. I gave you this discrete time. This was with the stems rather than the Dirac delta. Did you recall the difference between those two delta functions. This is, what's this one called? The unit impulse, and it's got someone's name associated with it. I don't know if you did that. Kronecker, right? That's the Kronecker delta, and this is the Dirac delta, right? Okay, so we're going to be doing the Dirac delta here for this operation, which will more correspond to the physical system. Okay, so these are the two pieces we need. We're taking an impulse train, and we're multiplying it by our input signal x of t. I like drawing a picture just to keep track of what's going on here. Maybe I'll call that x tilde of t. No, it's not called. Let's call it the notation Professor Archak used was x sub p of t. So what that looks like is a train of, if the input is something simple, like draw a cosine there, xp of t, depending on the sampling period. I'll just draw in some samples here. Okay, so that's xp of t. So note xp of t is this train of impulses, each with a area, which corresponded to, like this value here, if this is x of 0. Well, maybe we can look. What is the weight of this delta function? Or the area of that delta function? It's at x of 0, so it has area x of 0. Okay. So what our goal is here is we want to figure out what is xp of omega, and have we lost anything? How does xp of omega, compare to x of omega? Or, looking at our picture back over here, if I have the spectrum of this sampled signal, can I generate a continuous signal that is the same as the original here? So I mean, this is the most trivial signal processing, where if I put in, I could ask you that. What's the best? You've done transfer functions, right? What's the engineer's favorite transfer function? There's two favorite transfer functions. I'll give you one favorite transfer function is 0, because then your calculation's particularly easy. What's the other favorite transfer function? 1. Yeah, okay. So that would be the question, like the most basic signal processing, or digital signal processing system, can I at least do an identity operation? Like if I should at least be able to build a box where I take an input signal, do nothing to it, and get back out what I put in. I'd like to be, if I can't do that, like I can't do just an identity operation on a signal, I'm going to be it's going to be hard pressed to do anything more interesting if I can't do identity. So that's the question we want to ask here. So we're going to compare the spectrum of the sampled signal to the spectrum of the input signal, compare to, and even better, can we recover x of omega from xp of omega, and under what conditions? If so, what are the limitations? Okay, so we do a lot of analysis on this to answer that question. It's a very fundamental question. So let's come back to I'm short one board. Really, this course should be taught with 6 boards. We will commit this to memory. Where's the switch for that? Is there a switch here somewhere to raise the screen or raise the board? I guess Professor Archak doesn't use the blackboard, right? So it's not a good sign. Yeah. Okay, I think we're out of luck there. Gonna erase this. Oh, I tried that. It's like really stiff, and then we lose what's behind it too. I didn't see the switch to raise the screen. Okay. Keep this picture in mind. At least it doesn't have any math on it to refer to, so just keep that in mind. We'll continue with the analysis. Oh man. Okay. So my goal is to calculate what find xp of omega. Okay. So to do that, I need to find, I'm given x of omega, but I need to find p of omega. P of omega is just the Fourier transform of p of t. So this is 1 over 2 pi p of omega convolved with x of omega. Fourier transform p of t, just going to define that as p of omega. And have you done the Fourier transform of the comb function? Not so much. Okay, so you can get yourself in a bit of a tight corner if you don't use the right way of doing this. Maybe I'll show that just for the fun of it. So this Fourier transform of p of t is the Fourier transform, the summation over k delta t minus kt. So if you want to do this like a really complicated way, I know that the Fourier transform of the sum is equal to, by linearity, sum of the Fourier transforms. So this is not the way to do it, hard way. This is equal to the sum over k Fourier transform delta t minus kt. It's a good review. We're not going to do it this way, but just to show you what ends up. What is the if you delay something in time, what happens to its Fourier transform? So Fourier transform of x of t minus t naught. What do we do to it? Yeah, so it's e to the minus j omega t naught. There's your time delay x of omega. This is delay. So we're going to do this. So the hard way to do this is do this summation. It's like, oh man, this is now going to be summation k of e to the minus j k omega naught t. That's not too useful. We don't really want to work with that, but you might recognize that. It looks very similar to what? Something else you've seen before. Fourier series, right? So that's what we're going to do is we can take the Fourier series, then take the Fourier transform, and then the impulse train becomes clear. So Fourier series for p of t. Let's just brute force it so I don't have to remember anything. So it's going to end up with some summation a sub k e to the j k omega naught t, right? K is minus the complex Fourier series. How do I find a sub k? So how do I find the Fourier series coefficient given I have a periodic function? Do I just know what the Fourier series coefficients are? So 1 t, 1 over t, and we take the integral over a period of p of t, but I know what p of t is. It is just our summation here, so just one period, delta t minus t, and maybe I go from minus t over 2 to t over 2. Remember, I can choose whatever, as long as I take a period, I can shift that period around, so much easier to, do I want to take the integral from 0 to t? Probably not. Then I get I get half a delta function at 0, another half a delta function at t. So let's just switch from minus t over 2 to t over 2. Makes it much easier. E to the minus j k omega naught t dt. Oh, this is simple. This is just, we're going to pull this out. Just going to evaluate this at 0. To me, that just looks like 1 over t. Okay, so p of t coming back here. P of t by Fourier series. Oh, just 1 over t. So my a sub k for the Fourier series is just 1 over t. So it's just 1 over t summation e to the j k omega naught t. K is minus infinity to infinity. So now we can do p of omega. Now we can do term-wise Fourier transform. So it's 1 over t, and the Fourier transform of e to the jk omega naught t. It's Fourier transform of 1. Should just be, is that just 2 pi delta omega? Okay. So what's this Fourier transform? Yeah. So Fourier transform e to the j k omega naught t should just be 2 pi delta omega minus k omega naught. Right, so just doing the Fourier transform. Right, you can do this. The Fourier transform of this, right, just goes to the delta function. Does everyone recall that? Yeah, okay. Okay, so now we can do this Fourier transform term by term. We get a 1 over t. The 2 pi comes out from inside. 2 pi summation delta omega minus k omega naught. And for consistency with the notes, I like omega naught. For consistency with the notes, all these should be omega s's. Dang. So sorry, I've switched that variable from the notes, omega naught to omega s. Should I switch back now? Or continue with it? Maybe I should switch. I'll switch to omega s now. So just for consistency with the notes. So we have a train of impulses now in frequency 0, omega s, 2 omega s, dot, dot, dot. And they have an area now of 2 pi over t. Hopefully we're in good shape here. Yeah. Okay. So we've got now the Fourier transform of the p of t. So again, what are we doing? X of t, p of t, xp of t. We can now do this. Xp of omega by the property we wrote before is 1 over 2 pi in the convolution. 1 over 2 pi p of omega convolved with x of omega. In the notes, doing this algebraically, I guess you can do that if you like. This is going to be 1 over 2 pi integral, yuck, it's infinity to infinity log x of j. And I just get I want to match up the right dummy variable. So we don't really want to evaluate this. It's much easier to see that we just have, if I convolve with a delta function, what do I get? It's the identity operation. But now the delta function is shifted in frequency. So what happens to my frequency component? Also shifted in frequency. So for every impulse I get there in frequency, at multiples of frequency omega sub s, I'm going to get a copy of the original signal, but it's going to, because of this 1 over 2 pi factor here, that 1 over 2 pi is going to cancel with a 2 pi over t, so I'm going to get scaled by 1 over t. So x, let's look at a particularly simple spectrum. Like everyone uses this. We're going to be doing a multiplication and shift here. We've set up the problem to make it nice and easy. I've used, I should ask this. What are your favorite kinds of signals for making life easy? So you don't end up with a lot of J's floating around. Yeah, we all use real and even, right? So I'm going to come up with a real and even. So just to be cautious that not everything's so nice. But if it's real and even, I don't have to worry about the imaginary component. I'm just going to get copies here. So I'm going to assume a very nice very nice spectrum for x of omega, real and even for ease of calculation. I'm going to do a triangle here. This is omega. Let's call this omega sub m minus omega sub m. And what height do I want? I'll do a height of 1. And this is x of omega. So another thing I noticed, the notation changes. Professor Archak has been using the notation x of j omega. I've been using x of omega. I did have a little thinking about that, but I noticed you don't write delta of j omega, but you write x of j omega, but not delta of j omega. So I'm going to stick with just x of omega, so I don't have that j floating in there because it seems a little inconsistent to me. But follow Professor Archak's notation and just do a little substitution there. It doesn't change the pictures at all. So we're calling it x of omega. Okay. So, as we said, we're convolving with this function. Remember the 1 over 2 pi. So we're going to get a copy at each location here. So we have two cases in general. What's going to matter here is how wide 2 omega m is. What matters here? It's going to be the width of 2 omega m. That's this width here, right? It's width 2 omega m compared to omega sub s. Because the picture is going to change dramatically depending on the width of that triangle. And let's go to here. Okay, let's draw 2 pictures. Picture on the left. Let's start with the easy case. So I'm going to take copies of triangles, and I'm going to assume that this 2 omega m is less than omega s. Okay, 0. Let's do the first one. What's its height going to be? After doing this convolution operation? 1 over t. So again, 1 over 2 pi canceled the 2 pi over t, and we are convolving in the frequency domain. We don't have another 2 pi coming in there. We've already taken care of that. Okay, another point of interest here. What is this frequency? or another way to ask this, is this convolution with the delta, does it change the width of the function in any way? So convolving, I'm just looking at this one piece here. I'm just doing x of omega, say convolved with 1 over t delta omega. That's this term right here. So has the width changed at all? No. So there's no change in the width. So this point here is exactly omega m. This is minus omega m. Okay. So you have to. The point sometimes people get confused at this operation here does not change the width at all. So you have to keep track of the bookkeeping, keep track of what the two frequencies to keep track of here. Usually one is the edge or the width of this triangle, and the other is the center frequency. So as long as you keep track of where those two things are, those two numbers, you're in great shape. So I'm going to say 2 omega sub m is much less than omega s, or just a little bit less than. So let's put omega s right over here. This term will correspond to x of omega convolved with 1 over t delta omega minus omega s. So again, all it's going to do is going to shift, provide a copy of this triangle, which is shifted. Now it's centered at omega sub s. Going to have the same height, 1 over t. And now you need to do the little bit of bookkeeping. What's this frequency here? It's just omega s minus omega m. Okay. So notice this works in our favor here. So since omega s is greater than 2 omega sub m, omega s minus omega m is still greater than omega m, I have this space in between here. I think sometimes we might see that called like the guard band. It might not be quite the right term. I'll use it a little bit recklessly, that the sort of in talking about signals that they don't interfere with each other, you put in a band, a guard band, so that there's no overlap. This comes in from practical considerations. If you don't have an ideal filter, you make sure that there's not bleed through from one signal to the other. So for example, with cell phone signals, you have adjacent channels and you have a little space between the channels so things don't bleed over. Okay, question on case number 1. Let's do case number 2. Now I'm not going to have this constraint here. I'm going to say that 2 omega m is greater than omega s. Oops. So let's continue. Let's start drawing the picture the same as we had before. So here's another question. So when doing this math, does the math care about the relationship between these signals? The math doesn't really care. It's like your picture will care depending on those numbers, but the math works. The math works exactly the same way. So you follow through with the math, and the picture will tell you if something strange is happening or not. Yeah. Oh, we'll see that part of it is. So let's draw the picture. That's a great question. So actually part of the signal will be okay and part will be messed up. You're seeing there. So yeah, let's just draw. So we're just doing the first copy just as before. Omega minus omega m plus omega m, and again 1 over t. And now I'm going to deliberately, if this is omega m, here is 2 omega m. So what I'm saying is, 2 omega m greater than omega s. I'm going to put omega s like right in here, and maybe I'll even put a different color chalk there. So now I'm going to blindly, what does math say? Math says take a copy of the original signal. This is x of omega. Place a copy centered at omega sub s and scale it by 1 over t. So that's what I'm going to do here. Just like so. And now maybe this point is okay. Where is this point located? It's omega s plus the original width here. So it's centered at omega s, and then it goes to the right by omega m. So this is omega s plus omega m. The point I did last time, we can do the same one here. This point over here is still omega s minus omega m. Okay, but now something's going on different in this picture from this picture, and what's happening is we have the right edge of the signals of the spectrum centered at 0 is bleeding in to the left edge of the copy of the signal centered at omega s. This continues as well over here, the next copy at 2 omega s. Remember, it's an impulse train, so we're going to get more copies over here. It's another copy here, another copy here, another copy here. We get this, which is called aliasing. And that represents basically information that's been contaminated. If you knew a lot about your signal, you might be able to recover something about what's going on there. But in general, if you had like a random signal, like some speech or something like that, it's almost impossible to recover what's going on in this range once it's been overlapped. Because what happens is that the low frequencies of your signal get added on top of the high frequencies of the signal you want. If I continue the picture over here, this is periodic. Oops. All right, so it just keeps going. So there's infinitely many copies, each scaled by 1 over t. So let's go back to your question. Did we answer it, or? Let's see. So it's hard to picture what this is. This is actually like in time. It's a sinc squared. It's not a very obvious signal. So one of the more simple signals to think about is something like a sine or a cosine. Like a cosine would be an easier thing where you're sampling a cosine. So what this picture means, let me jump right to that. That's a really good point. It's like I've got that question before, because it's a triangle. What does that look like in time? There's no intuition for what that looks like. So it's a simple example, like a cosine, sampling a cosine. Oh, and let me not even do. Let's just do some sampling here. What's the Fourier transform for cosine 2p look like? 2 deltas. Yep. What's the height of the delta? Or area of the delta? 1/2 times 2 pi, isn't it? I'm going to, if I trust this, I'm going to go with pi. I'm going to go with pi here. Okay. Okay, let me just draw in my cosine. This will be 1/2. This is 1. So cosine of pi is -1. So let's draw a nice. Okay. So what would you say omega sub m is in this picture? 2 pi. All right, so you can imagine, oh, here's the, instead of drawing that triangle in there, I'm going to do a cosine, which is easier to see in time. So my maximum frequency in my cosine is 2 pi. Okay. So for the picture on the left, what can you tell me for what should omega s be? What should omega s be, like say the smallest omega s for which this is, we're in this case number 1. Isn't it just omega s? Let's just flip this around. Omega s should be greater than 2 omega m. Right? This is a boundary condition right at 4 pi. So I'm going to make things easier. How about, why don't I pick omega s, instead of picking omega s equals 4 pi, how about omega s equals 8 pi? Okay, so how does omega s relate to my sample interval? Just to ground this back, how far apart are my my samples in time if my omega sub s is 8 pi? How do I go from period to frequency? 2 pi over t, right? So t sub s is 2 pi over, actually I'd usually do it the other way. Omega s is equal to 2 pi over t sub s. So tell me what t sub s is. I think it's 1/4 of a second, right? T sub s. 2 pi over 1/4 is equal to 8 pi. Oh, so here's my samples here. So I'm going to get a sample. I'm very glad I did this. Otherwise, you would see I'd just get a sample like here and there. So I'm going to sample at 0. I'm going to sample at 1/4 of a second. That's right here. And there's a sample. If I wanted to draw my impulses, make it accurate here. This is my p of t. Another sample here. A sample at 3/4. There's an impulse. And another sample there at 1. Okay. So there's my p of t. And you could see, maybe this makes a little sense, that we've got sufficient samples. Oh, okay, yeah, I could kind of see that that's a cosine if you gave me those four points. If you told me there's a smooth curve of without any wiggles going through those 4 points, yeah, it's cosine. Okay, so this part makes sense. Okay, so now let's violate this. If this part makes sense, then let's violate that. So this is we're doing here case number 1. Let's do case number 2. We got this. Let's pick something easy. So omega m is 2 pi. Let me just pick a bad case. I think we had another case here. Oh. Okay, let's do, no, we're actually on example 1. I'm going to pick omega s is equal to instead of being twice that, instead of being 4 pi, I'm going to let omega s equal to 3 pi. Okay. So now omega s is 2 pi over t sub s, or t sub s equals, looks to me like 2/3. 2 pi over 2 pi. Yeah, looks right. 2/3 of a second. So let's see. Do we sample there? Let's draw another picture. Half, 1 quarter, 3/4. This is good stuff. This is the Hagoromo chalk. I read about this. This is the primo chalk. Look at that, beautiful. All right. So here's our original signal, and now we're going to be sampling it at 2/3 of a second. So we have a sample at 0. Ooh, 2/3 of a second. Wow, that's terrible. Okay. The picture's looking a little weird. Is that right? 2/3 of a second? 3 pi. 4 pi, 3 pi. So, wow. That is so terrible. Okay, I'm going to do it. So here's 0, and 2/3 of a second is 2/3 is between 1/2 and 3/4 somewhere here. So there's a sample at 2/3. This is t. So I'm going to get this sample and this sample. The next sample is going to be over at 4/3. So let's continue this. So we'll go to 3/2. 4/3 is less than 3/2, right? 1 1/3 less than 1 1/2. So somewhere in here, here's a crossing max. So somewhere here. There is 4/3. Okay, so I have a sample here, and I have a sample here. Sample 1, sample 2, sample 3. Now looking at that, that doesn't look at all like the original cosine. And in fact, we can look at it from what the Fourier transform is telling us. So what we're going to do is take those two spectra, and so instead of dealing with, take the spectrum of the cosine, take the cosine spectrum, that's our new x of omega, we're going to apply these two rules. So we just looked at it in the time domain, we didn't look at it in the frequency domain. So let's go back and add in the frequency domain. Okay, leave this here. So this is xp of omega, recall, which is the spectrum of the sampled signal, the spectrum of the signal multiplied by the Dirac delta function. Omega. So start at 0, that's always the easiest one. So we get one copy of my original spectrum, centered at 0. Okay, so this is at minus 2 pi, and this is 2 pi. What is the area of those impulses? A little bookkeeping. Keep track of the coefficients, keep track of the amplitude. When we sample at time, what happens to the amplitude? There's a 1 over t factor, right? Just like the triangle got scaled by 1 over t. So this becomes pi over t, pi over t. Okay, that's the original signal. Now there's a copy. Where is the copy centered? So remember what we're doing when we're multiplying in time by an impulse train. In frequency, we're convolving with an impulse train, and so the convolution with a periodic set of impulses just gives us periodic copies of our original signal. So just here, the first copy is at 0. The second copy is right at omega sub s. And we said here, omega sub s is equal to 8 pi. So we'll get a copy. So here's 2 pi, 4 pi, 6 pi, 8 pi. I have a copy centered at 8 pi. And notice, so where does that minus 2 pi appear? So the easy part, the 0, where does the 0 go to? 0 goes to 8 pi, so the minus 2 pi has to appear 6 pi. Okay, and that's at 10 pi over here. So remember this frequency, we did that before, that's just omega s minus omega m. So that's minus 2. Okay. So what do I have here? I have separation between, this is a cosine, and then this is a copy of the cosine. Kind of jumping to the punchline. I'm going to go a little over the break. To the punchline, we'll talk about how do we recover the question we started out in the beginning. How do we recover the original signal? So to jump to the punchlines, you see where we're going on here. We're going to apply a low-pass filter here. So apply a low-pass filter to the sampled signal and ideally end up back there. So that works in that case. Let's see case number 2, and then we'll take a break after this. Okay, same picture, same construction as before. Omega. This is, again, xp of omega, but now with omega s equals 3 pi. So always start with the 0 frequency. Nothing has happened to that. You always just get an original copy centered right where it started. So minus 2 pi and 2 pi. Again, the area is pi over t, pi over t. 2 pi. Let's expand this to make it a little bit more legible. Minus 2 pi, 0, 2 pi, 4 pi, 6 pi, 8 pi. So I said we have our original copy, pi over t, pi over t. You get another the next copy is centered where? Yeah, it's centered at 3 pi, right? So it's always centered at multiples of the sampling frequency omega sub s, which is right here. So let's make a note of that. That's omega sub s. Note before, omega sub s here, this is omega sub s, 8 pi, way over here. So I need another, just because it's particularly, since it's so nasty, it gets the yellow shock. Okay, we have a copy that is centered at omega s, which is equal to 3 pi. Where did this left delta function end up? It's 2 pi to the left of the center. So 3 pi, where's it going to end up? Pi. Look at that. And where's the right side? Where does the right side end up? 5 pi, right? And then we're going to get another copy centered at 6 pi. Oh, that's nasty. So 6 pi minus 2 pi. There's another copy here, 4 pi and 8 pi, etc. Okay. Coming from the left, we would also have a copy here. So these yellow ones, these are aliased copies of the original cosine. So the punchline. We take a low-pass filter. the low-pass filter is always related to what your sampling frequency is. We choose a low-pass filter which has a cutoff of half the sampling frequency, so, or maybe a little bit more than that. So here's a low-pass filter here. That's what we would use to recover the original signal. So it's lost, it's whatever frequency this is. If I go backwards now on this signal is going to be pi over t delta omega minus pi plus delta omega plus pi. So that is, what's the time function corresponding to that? It's cosine, what's the frequency of the cosine? Yeah, cosine of pi t. So instead of, so now cosine of pi t, so at 1, it's basically where this one was at a half. So comes down here. The other sample is here at 4/3, like that. Okay, so this is what we would call the reconstructed x. Let's call it x tilde of t, which would be the low-pass filter of xp of omega. And notice what happened. We started with a cosine at basically frequency of 2 pi, and we ended up with a cosine at half the frequency, and that's the aliased. So it's much easier to see, I guess, with a sinusoid than it is with the triangle. So questions? Yes? Is there any band limited? Yes. So if the original signal is band limited, and then you can reconstruct it, given that you have a sampling frequency which is a little bit more than twice the highest frequency contained within the signal. That's exactly right. If it's not band limited, you might use some side information. So, if there's some other information about the signal, there's this sort of this compressed sensing technique. Like if we tell you something very specific about the signal, for example, if I told you I'm going to give you the sample at 2/3 of a second, and I'm going to tell you the original signal was either cosine of pi t or cosine of 2 pi t. Well, if you tell me that there's only one of two choices, then I can use that one sample to distinguish between them. So if you bring in all the side information, then you can do a little bit more. But in general, if I just say, I don't know what the signal was originally, all I can tell you is that its maximum bandwidth is this amount, and you give me twice that maximum frequency of samples, then I can recover it with an ideal low-pass filter. Exactly. Great. Other questions? Good. Okay, let's take it. What do you do? What, a 5-minute break, 10-minute break, 20-minute break? 5? What's the normal, like 5? Yeah, let's do 5. We'll do 5, yeah. So I heard Professor Lustig visited this class. Is that correct? Yeah. And a visit from Professor Lustig, you get to tell you about his course and the cool projects you get to do in the DSP class. I didn't bring a slide for it, but also tell you 128 is a follow-on course here, the feedback control. So it does a lot of cool stuff where so in signal processing, well, I'm maybe a little biased towards control. And like signal processing, you're sort of like this passive observer, and this information comes by, and you try to make some sense out of it. In control, we grab the world and we force it to do what we want it to do. You get a lot more action in control. just put it that way. Another course you can take, which 120 is a prerequisite to, which I'll talk about, take some of your time today, is a mechatronics design lab, which I teach in the spring. This is a hands-on design course which combines all sorts of things. Combines signal processing from 120 there's a line camera, we find a path. It combines control. You don't need 128 as a prerequisite. The prerequisite is just 120, 16A, 16B, and the programming in C. We have a onboard processor. We can run Linux. We got have Python remote things. We got Wi-Fi. We got 4 gigabytes of memory on there, so you can do all sorts of really interesting things about recording the path of the car and then using that to control how the car works. It is a hands-on course. If you're looking for a chance to build circuit boards, make motors work, power supplies, sensors, control everything. As well as software, this might be of interest to you. And this was a video made by Emily Chen back in 2014. She did a great job, so I keep showing it. So it gives you an idea of what the control task is from the car's point of view. So that's how fast the car is going. It's going at about 3 meters a second. This is in the courtyard before the tea room was there. So you get very, it's challenging compared to let's say driving a Google car, because you don't get the view ahead of time. You really get a view of just a few car lengths. So you have to respond very quickly. The cars are running pretty close to the friction limit, so the cars will drift. So at the end of the course, there's internal competition. We also go to Davis, and there's intercollegiate competitions. A lot of the other UCs are there. So it's intended for seniors. Juniors are welcome to take it as well. Sort of call it a capstone design experience. So it's good. I think a lot of the students who take it enjoy it a lot, because they get something very concrete every week. They're building something and getting it to work. So I'll just put in there's running on carpet. So it's we break it down into pieces. So even if you don't know one particular piece, is every week it's like, okay, we're doing power supplies this week, we're doing motor drives this week, we're doing signal processing this week. So it's all broken down. So the intent is that students will, they know things from their prerequisite courses, but then we go into the details you need to actually make stuff work. So hopefully some of you will find that of interest and consider taking that either now or next, or a year from now. So there's a front-facing camera. It's a line camera that's reading at somewhere around 200 frames a second. It's just a line camera. Some students will put multiple line cameras on there, so you can actually get from 2 cameras. You can get some sort of first difference. If you do the first difference between the 2 cameras, you can actually get a lateral velocity. So you can do some interesting signal processing there. So let me blank this screen. Okay. So where were we? We talked about the sampling, we talked about the spectrum, and I gave you just sort of a hint that when we want to recover back the original signal, we're going to apply a filter called the reconstruction filter. So I want to spend some time now giving some detail on what is the nature of the process for recovering the original signal from its samples. That's the reconstruction process. Let's go back to which board? Do this. So the idea is just going back to maybe so we don't lose track of the picture here. There's xp of t. xp of t is this ugly, like for the cosine, right? It's this ugly set of impulses. And again, we're not going into too much detail on it, leaving it at a conceptual level. So this is like a mathematical artifact. The signals inside your computer are not impulses floating around. Right? This is just a mathematical representation of, as we said here, right, some xd of n, those discrete numbers. Okay. But we're treating it as impulses because then we can deal with it all very nicely with the continuous time Fourier transforms. You can also look at it once it's sampled. Of course, you've probably already done DTFT and 16a, 16b. Probably done DTFT. Okay, but this is they all end up being the same. Just looking at Fourier transform, continuous time, continuous frequency, going to DFT, which is discrete time to discrete frequency, and discrete time Fourier transform would be discrete in time, continuous in frequency, but periodic. You probably see now from this convolution, we're convolving with a periodic function in time. That's why we get periodic frequency spectrum. Okay, so dealing with this, we'd like to get back somehow, mystery box, we'd like to get back xr of t, the reconstructed signal, which we hope, at least in the case of this this cosine, will come back something like this. Where again, if this is 0t, 2t, this will be 0t, 2t, etc. So it's actually, I always found this somewhat of a magical, mysterious thing. But look at how sparse this signal is here. I've got a peak, the zero crossing, a negative peak, zero crossing, peak, and there exists this magic box here, which you feed in those few pulses and you get out this beautiful cosine. Well, in this frequency domain, maybe it's not so mysterious. So look at the sampled signal. Go back to our triangle. xp of omega. Let's do case number 1. We're calling that, remember, omega s greater than 2 omega m. Zero omega s, 2 omega s. This is just the picture you have on the left board there. Minus omega m plus omega m. And more copies. And not 3 dots, just mean it's periodic. Continuing. Okay, so all we've done with the sampling, at least in this picture, is taken our original signal, scaled it by pi over t, and made these extra copies at omega s to omega s, etc. So how do we get back, if I wanted to get back just my original x of t, how to get, that's the question, right? How to get xr of t equal to x of t. Do I want to keep those extra copies? No, I want to throw them out. How do I throw them away? Low pass filter. Okay, so low pass filter, that's the main thing here. So I will apply a low pass filter right here, and I'm going to put it, this one is, you have to worry about this later, we won't worry about it at the moment. My triangle is very nicely situated so that it's 0 at the edge. So if my ideal low pass filter is exactly hitting that 0 multiplied by a step, I don't have to worry about it. Sometimes you have to worry about it, like if I'm low pass filtering a low pass filter, I end up having to stare at that for about an hour or two to have it make sense. What does it mean to low pass filter? Because what I'm getting at is if I take this and I multiply it by this. What does that what does that do? I've got two step edges multiplied by each other. We don't have to worry about that for this case because I've made it 0 at the edge. You also have to worry about this if you do an ideal low-pass filter exactly at the edge. If my box width goes exactly through the Dirac delta function, which corresponds to the cosine, again, you just get into a little bit of a mess here. So I'm not going to worry about that now. This is very convenient. I'm going to just pick here omega sub m minus omega sub m, and whatever's happening at the edge doesn't matter because it's multiplied by 0. Okay? And then I just need to fix, how do I fix the amplitude? So my original triangle started with 1, so I just need to fix the amplitude. If this was pi over t, I think I'm just going to multiply by t over pi, right? So just a scale factor there. So now, at least for the input signal of a triangle, I sample it, pass it through a low-pass filter. This is the ideal low-pass filter. And I'll get back to my original signal. Question? Great. So that's a great question. The question is, how do we know what frequency to choose here? The constraint comes here. So I want to have my cutoff frequency less than half the sampling frequency. So that's a little bit more general choice, is I could have this omega s over 2, or a little bit less than omega s over 2, and then anything that's less than half the sampling frequency will come through, get reconstructed. Exactly. Good question. Other questions? Okay. So that's what's in this box. See if we get a little. It's a little magical. I think this is, we end up with the time. What's the time function that gives us a box in frequency domain? Sinc. Yeah. So it turns out that this sinc is this ideal interpolator. It will, if your signal is band limited, the sinc function will provide an ideal, perfect interpolation between any of your sample points, which is surprising. It's like, how does it do a good approximation? No, it does perfect if your signal is band limited. And it's very peculiar too. If you think about, you've probably done interpolation, like people have done straight line interpolation, right? You get 2 points, you find the point in between. So to do interpolation between 2 points, I take this point, right? Just do the slope and everything in between. The sinc interpolation is very weird because it says the value, the intermediate value between these 2 points depends not just on these 2 points, but on stuff going out to minus infinity and plus infinity. We'll have an effect here. By the way, did you do this? The property. If a signal is time limited, is it band limited? Did you do that property? If a signal is limited in time, it cannot be limited in frequency. Maybe the other direction is easier. What if you have a spectrum where there's just one frequency, like a cosine? Can a signal which is band limited, such as a cosine, can it be time limited? No, so it turns out right. So cosine is not time limited, but it is band limited. So this interpolation is very weird. We have a ideal low-pass filter here, which is limited in frequency. Since it's frequency limited, it's not time limited. The time extends everywhere. Very weird. Very weird. So when you're doing this interpolation, which is one of the magic things, it's pulling things out from all over the place. So let's see what the picture looks like. Reconstruction filter. might also call it ideal interpolation, ideal sync interpolation. Let's see what we get. Okay. Pi over t. Negative pi there. Sorry, I made a mistake here. The scale factor, I had that pi floating around from the cosine example. 1 over t. There's not any pi here. Sorry about that. This is just t. This t, I was looking at... Sorry, my cosine example had an extraneous pi floating around, so the pi is not there. It's supposed to be just a 1. So the ideal interpolation filter is just this, height of t, and what limits do we want? Oh, we can go all the way up to omega s over 2. Okay. Whew, do we want to do the inverse Fourier transform on that? I'm like looking at that going like, yeah, we want to see it. We want to see the... Should I just write down the formula? Do you want to see where it comes from? Just go to the sink. Yeah, just go to the sink. Yeah, okay, let's just go to the sink. Okay. So this corresponds to... So this is h, let's call it h low pass of omega, has this frequency response, so the time function is t omega sub s over 2 pi. T is just our scale factor. Sync omega s over 2 pi t. Okay. Okay. So are we defining sync as sine pi x over pi x or sine pi x over x? Are we defining it like that, or is it got a pi in the numerator and the denominator? Okay, great. Okay, so t omega s over 2 pi, I don't know. Would rather write this out over 2 pi t times pi over, same argument here, omega s over 2, the pi's cancel. Oh, omega s over 2 t, great. Let's check. This is h of t. Let's check h of 0, if I did this right. I guess over 2. So this term just becomes 1 as you take the limit. So it's t omega s over 2 pi. But omega s is 2 pi over t, correct? It was 1. Okay. Okay, all the pi's worked out. I'm happy about that. Okay. Now, we just need to find the zero crossing. So we know it's going to come down and do some zero crossings. The first zero crossing is zeros at sine of what? Sine of what equals 0? Sine of 0 equals 0, sine of pi. Okay. So next zero crossing. Omega s. Sorry. Yeah. Right? So t is equal to 2 pi over omega sub s is 2 pi over, and omega s is 2 pi over t sub s equals the sampling time. Okay. Okay. The next zero cross, so we have pi, 2 pi, 2t sub s, 3t sub s. This is the zero crossing, and it should be like so. I'm going to check my notes and hope I got it right. The important thing to note here that people sometimes draw this wrong is that the width here, and maybe I should have made it a little clearer, the width here is twice as wide as that separation there. Okay, I think I got it. I got it, okay. So this is the interpolation function, and it's actually kind of pretty interesting. Notice that there's a zero crossing at negative t sub s minus 2t sub s minus 3t sub s. So there's all these zero crossings exactly at the sample interval. So maybe with a simple signal like a cosine, which is sampled exactly at those times, we might see what's happening. Oh. Okay. So the low-pass filter and frequency just corresponds to multiplying these spectra. If I want to see what's going on in the time domain, what do I have to do with this impulse response? I have to convolve it, right? So I have to convolve this with my samples and see what I end up with. Maybe with a... Maybe we should go back to the cosine and see if it at all looks plausible. So let's see. Cosine example. We're doing cosine 2 pi t. This is an example. And let's do omega s is equal to 8 pi. T sub s is 2 pi over omega sub s is equal to 1/4. Okay. Cosine period of 1. Oh, that's okay. And we're going to have a sample every 1/4 of a second. This is not too bad. So sample here. Oh, let me give myself some space here. Or even better, I will draw it really small so you can't tell how inaccurate I am. That might be a safer thing to do. So here's a sample. So we're going to sample multiply by Dirac delta function. Okay. So there's our samples at 1/4 of a second. So I'm going to convolve. I'm going to just say x r of t is just h LP, whatever I call this, h of t. I just put HLP of t convolved with xp of t. So this is xp of t. This is our sampled cosine. So I just take a copy. At least for this case, the convolution is simpler than usual because I'm just going to get a copy. Each impulse in time will correspond to a copy of the sinc function, and I don't have to. And the scaling of the sinc function is pretty good. This is just 1 or minus 1. So I'll get a copy here. So I'm going to take a copy of this sinc function. I get one copy centered at 0 with a scale factor of 1. Another copy centered at 0.5 with a scale factor of minus 1. And another copy at 1. Right? Scale factor. So the tricky part here is I just want to be careful doing the bookkeeping that I make sure that these zero crossings add up in a nice way. This example is like the simplest one. Everything works out great. The zero crossings, I'll tell you ahead of time, are going to line up so I don't have to worry about adding things up in between, at least at the zero crossings. This gets remarkably complicated if I had, let's say instead of a 1 hertz cosine, I had a 1.3 hertz cosine and a 7.2 hertz sampling frequency. This just would be hard to see what's going on. So let's put a copy here. We're going to put a copy scaled, and the zero crossing is at t sub s, but t sub s is 1/4 of a second. So let's do that right here. That works out nice. 0. So this is t sub s. Comes down like so. I kind of exaggerated. It's coming off as 1 over sort of 1 over t. So it's not decaying all that fast. You do have to be careful about it, but it's not necessarily. It doesn't become negligible for quite a while. So here's one copy. So this is the copy. This is just h of t. I'm going to get another copy, which is going to be h minus h of t minus 0.5. That'll correspond to this one here. Okay, so it comes down here, minus 1. The zero crossing, see it's very fortuitous. Zero crossing lines up there, zero crossing lines up there. Zero crossing lines up there, and this continues. Okay. Question on the second copy. Third copy, centered at 1, right here. It's again, now it's just h of t minus 1. Same height here. Zero crossing, cross. Keeps on going. Aha. Now, this is just 3 copies. So I could consider here, this is the I have a copy from at 0.5, I have a copy of the sync from 1, I'll have a copy of the sync from 1.5, 2, etc. All of those will add together in an interesting way with diminishing returns here. You can actually see that you get a series there, so it's going to be like 1 over k plus 1 over 3k, 1 over 5k. So you're going to get something sort of a diminishing series there. Some are plus and some are minus. So what happens is that this sync function is not really a cosine, and all these other little interpolating terms that are added in from these extra copies combine together in I think, a pretty remarkable way to turn this from sine x over x into a true cosine. So it actually comes, so I get something here, and the zero crossing is the same, right? And it'll end up following a true cosine by adding together all those copies. So that's how the interpolation filter works. A little bit of the intuition behind, at least for that simple signal, how you could possibly get a cosine starting from those alternating samples, alternating +1, -1 samples with a zero sample in between, just using the interpolation filter. Okay, questions? Yeah. This is from this picture here. So the signal is sampled, it's discrete. That's right. So this is right here. Yeah, the discrete signal goes through that filter. This is the time domain representation. Yeah, and then it gets. This is the time domain, and then that gets convolved with this XP. Exactly. Great. Other questions? Okay. So again, we have all these things are idealizations so far. We have ideal Dirac delta sampling. We have ideal low-pass filter reconstruction. They're all like sort of, yeah, that's the best case if you can actually, you can't actually get that. So we do need to consider making things a little bit more realistic. And this I started off in the beginning with the sample and hold. So sample and hold could be used for the sampling stage as part of your analog digital converter, and the equivalent of sample and hold can also be used in the output stage, an equivalent of the digital to analog converter. So before we go through this reconstruction filter, well, what is the computer really outputting? So maybe I'll draw that picture again. Yeah, okay, let's draw it here. X of t, a to d, CPU, and our low-pass filter. We're going to call this XR of t. So what I want to introduce is what is this digital to analog converter doing? So digital analog converter is taking the numbers in the computer, xd of n, and converting it to, let's just call it xd of t. The D-to-A converter has, again, something similar to a, actually I can explain the digital analog converter. The simplest and cheapest digital analog converter you could have is just a ramp generator, and you have a voltage ramping up here, and you close the switch whenever the voltage reaches the value you want. So now you have, let's say I want 3 volts and I've got a ramp that goes from 0 to 10 volts. I just let the ramp go up. When the ramp gets to 3 volts, I just close the switch. If I know my ramp is going like 1 volt per second, I just wait 3 seconds and I'll get the voltage I want and go through this sample and hold. So this signal here, because of that sample and hold, actually looks like this, and we call this the zero order hold. Sort of a series, like a staircase. So how would I go from sort of this ideal set of impulses how do I go from this impulses xp of t to this thing here, xd of t? What mathematical operation would I? My input is this train of impulses. My output is a staircase. What's the impulse response of that system need to be? Very closely related to either a unit step or superposition of unit steps turns into a box. So I can represent this as a box, convolve this with, this is 0, this is t, convolve it with a box that goes from 0 to t, and I'll get this. You could also, steps would also work. We have to be a little bit, you have to do a little bit more bookkeeping. So here with this step, I just get copies of the steps. With a box, I get copies of the boxes. With the step, I have to do a little bit careful. Okay, so what this is doing is we have to now consider the effect of the zero order hold before now we do. So this is zero order hold here, and this is still our low pass filter to reconstruct. So let's see what that does. Oh, okay. So we want to look what happens in the frequency domain from the zero order hold. And what do we want to call that? Let's call that H naught T. So what this is going to do, this box is going to, in the time domain, it's going to hold the signal constant for one sample period, just like we think over here with the capacitor. So we need to consider what effect does this have on the frequency domain. So we need to calculate the Fourier transform of this. It's going to be the Fourier transform of a box. To make life easy for ourselves, let's say that this is a box which goes from minus t over 2 to t over 2, convolved with a delay of half a sample. And this will have a height of 1. What's the Fourier transform of a delay? Yeah, e to the minus j omega t over 2. And, well, we'd expect, again, as we saw before, the Fourier transform of a box is going to be, like, again, a sinc, but now it's a sinc in frequency, just for the fun of it. Okay, so sine omega t over 2 from tables over omega t over 2. Okay, so we're going to call that h naught of omega. And let's see, I don't want to sketch this phase term. This phase term makes things kind of complicated to keep track of. Let me look at just the magnitude, just to get an idea of what it's doing in our frequency domain without getting bogged down in the phase details. Okay, this is in the omega domain, and again, we want to keep track of the zero crossings. Where are we going with this? I'm just trying to. We already did the ideal low-pass filter. But now we're inserting this extra zero-order hold. We want to see what effect that has. Okay, so it's got, again, a peak of 1. Do we have a scale factor on top? No. Oh. There we go. Peak of t. The zero crossing is when omega t over 2 is equal to omega t over 2 is equal to pi, or omega is equal to 2 pi over t. Interesting. 2 pi over t, 4 pi over t. Minus 4 pi over t, and of course this continues. Now we want to compare this to our ideal low-pass filter. Kind of interesting. So, where was our ideal low-pass filter? What was the cutoff frequency for the ideal low-pass filter? Did we do it? We erased it. What was the cutoff frequency for ideal low-pass filter for reconstruction? Yeah, this is omega s over 2. This is minus omega s over 2. So the question we want to ask is, what? Now I've introduced this zero-order hold, which has its own frequency domain effect on our signal. We originally wanted to do an ideal low-pass filter, but now we have this combined. So I want to realize that this filter will be multiplied by this filter. This is also a height of. Oh, this was reconstruction with t as well, wasn't it? Yeah, it was also t. Where did that t come from? That's originally from the sampling. Remember, we multiplied by the Coulomb function. We got a 1 over t in there, so I'm canceling that out with this t. Okay, so these two have the same. Hopefully, I want to do that. Wait. Let's make sure they don't end up with too many t's. I'm not careful, end up with too many t's here. End up with too many t's. I don't want to end up with t squared. Okay. There's a t. Don't want to. I just want to multiply these. Okay. So what I want to relate is, where does my box go? Is my box bigger than zero crossing or smaller than that? So omega s is 2 pi over t. So this is equal to pi over t. So that's right here. So this is the ideal pass filter. So now, what's the significance of that? That's great. The significance of that is that now I've added some distortion onto my original signal. So the zero order hold, because of the sink, is causing this to dip down. So what do we end up with? So zero order hold plus ideal low pass filter, omega s over 2 minus omega s over 2, we end up with something that looks a little like this. So there's a little dip that'll cause a little distortion. So if we actually need to compensate for that, we need to compensate for the effect of the zero order hold in our reconstruction filter, or you can do processing ahead of time. You've got a digital signal processing algorithm. Since you know that the output is going to go into a system with a zero order hold, you know the frequency is going to be distorted like this, so you could pre-distort before it comes out. So we need to add a compensating filter. Something like sort of the opposite of that. So that the product of those two to get ideal. Okay. All right. Questions? Yes. Yes, this is the zero order hold. It's not intentionally. It's not put in there to perform a low pass function explicitly. It has effective low pass filtering things, so you can see like fast variations. Now you can't have it because of this step. But it's an artifact that's you can't avoid introducing it if you have a digital analog converter. It's because of that digital analog converter where the value is held. So the computer outputs a value, does some computations, outputs another value, and so that value is held constant in between the updates from the computer algorithm. So it's holding that value constant, has this interesting effect of this strange low-pass filter with these lobes like this. Sorry, I should have done the absolute value here. That's okay. So it's got this weird low-pass thing here where you've got all this high-frequency information coming through. Then that's combined with the reconstruction filter, but you're left with this artifact which was introduced by the zero-order hold. Exactly. And so this is going through the effect it has. Great. Other questions? Yeah. Oh, yeah, I didn't get to the last part that was in Professor Archak's notes. You want to look at that. So there's a variety of functions one can use for interpolation. One thing you can use is a triangle function, which acts as a linear interpolator. And so then your filter would be, triangle is a box convolved with a box. So that's a sinc squared. So if you use a sinc squared, that's like a triangle interpolator. So there's a whole family of interpolation functions one can use. And in fact, this ideal low-pass filter is sort of an idealization that you don't actually ever have. So you're always going to be using some approximations towards that. Great. So thanks, everybody. Enjoyed have a good weekend.
few quick questions. For the first low pass filter, it's